Okay.
Now we're home. There you go.
Okay. One more try, now we're online. Right. So yes, we have this, so Slack is like a sort of chat program that's heavily used by programmers. We have this one for general C++, but we have our own chat room in there, and you can chat to us whenever you like. Please do. Come and join the crush.
It's busy there.
Yeah. This is going to be interesting. You probably put those bits on the floor, but you might struggle to see the screen. But you do get the most comfortable chair in the room, so
People don't get such chair.
All right.
I think we'll do that, yeah. That's what I think. Just going to get extra chairs. It's just tracking.
That was our C license for that.
Oh, okay. Okay.
But thank you all for joining us, rather than enjoying the wonderful sunny evening. It's far more fun being stuck in a cramped room, right?
Let's be British. That weather is abomination.
Oh, far too hot. Yeah, much too hot.
As proper British person, we should sit in a pub with a pint.
Well, we can do that afterwards. Yeah, once it's cooled down a bit. Anyway, what do we got for those guys? We'll go through the same slides as we always do. This is the textbook. Hopefully most of you have got a copy of it by now. If you haven't, go to Amazon, go and have a look, or other retailers are available. So this is what we're doing today. First of all, we've got a bit of revision. So what we've covered in the sessions, not in great detail. But the idea of this is it's not just me standing here talking. Wait for them. It's not just me standing here talking. We want questions. We want. I'll say a few things and maybe prompt some questions, but really it shouldn't just be me up here spouting. And then as I was saying, we're going to have a little bit of a test, multiple choice online thing, just really for you to gauge how you're doing. And then we're going to go and we're going to have some a bit more sort of normal service resumed, which will be just me standing up here talking about standard vector, which is probably the most important of the standard library classes along with string. I originally wrote all. We're not going to cover all of it because there's a lot there, but we're going to cover the most important bits of standard vector. Does that sound good? Yeah, all right. So revision. Are these guys coming in or are they coming out? What are they doing? Yeah, if you hadn't gathered, the rooms that we're in is kind of beyond our control, so we've been lumbered with it. Yeah.
Can I ask you the password
Yeah, it's We Love Code. Right on the wall. Okay, let's start off talking about types. Who can tell me what a type is? Silence.
There's a way to define a bit of information like a string or a number or a boolean. It's a way to define.
It's a way to give meaning to data.
Yeah.
Yes, absolutely. You're both right. In fact, I'm pretty sure you just read that somehow that was about to appear on the screen, right? So your computer, your memory, it only deals in ones and zeros. And we don't know, well, without types, we don't know whether those ones and zeros, do they represent an int, do they represent a floating point number, do they represent a string? We don't know. I might just let
do
this
you want
happen
to stop
first.
for 2 seconds? Sorry, you've got a bit of a popular talk here, so I think it's all people.
Alright, I'll squeeze that in.
Okay,
Okay.
Get there eventually. Shouldn't show this. Sorry.
It might literally have to be a laptop. So we're the closest front row I've ever had.
Wow.
Oh, sorry. I can maybe move this back a little bit.
Go ahead. Yeah, go ahead.
So basically, what happened? The other conference have more people than us.
I don't know. I guess they must have.
Empty some of them. I don't know if it's late.
Yeah, they must have had more like pre-registrations than we did or something. I don't know.
Is my head blocking?
Okay, are we ready? Let's continue. Right. So your computer, the memory, it's just ones and zeros, and we need to have a way to give meaning to those ones and zeros. Right. So even if you're not familiar with with programming, you are familiar with this idea, almost certainly, just from the file system on your computer. Because again, your hard drive just holds ones and zeros. But you're familiar with the idea of a file type. So you can have a PDF file or a Word document or an MP3 or whatever it might be. And that gives meaning to those ones and zeros on your disk. And if you try and open a PDF with your music player, it's not going to work. Right? And if you try and force it on Windows, if you change the file extension and you try and open it, you're just going to get garbage because it's not a meaningful pattern of memory. So that's what a type is, or at least in C++. It's a way of giving meaning to our data. So yes, we can multiply two numbers, we can't multiply two strings. C++ is statically typed. So every variable has its type determined at compile time, either because we've told the compiler what it is or it's deduced what it is. And it's strongly typed. It's not duck typed, is the alternative. So once a variable has a particular type, it can never change. Does that all make sense? You've got to yell at me, you've got to shout questions. Yeah? Alright, so that's it, that's types. We've got one slide on everything, so this may go in about 10 minutes if I'm not interrupted. Functions. Every function in C++ returns 0 or 1 values. Okay, so same as C or Java or C#. Other languages like Python, you can return multiple things in a tuple, but in C++, if we have nothing to return from the function, then we write the return type as void. Functions can take 0 or more parameters. Okay, the parameters, if you remember the difference between the parameters and arguments, the parameters are the things you put in the function signature, the arguments are the things you pass to the function. Every parameter, we need to tell the compiler what type it is. And usually we give it a name as well. The name is, strictly speaking, optional, but if you don't give it a name, you can't do anything with that parameter. So. There's one thing I didn't mention when we were doing this before, is we have this notion of default parameters as well. This is something that isn't in C, it's only in C++. So if we call a function with fewer arguments than there are parameters, but we have given default values, then inside the function, that parameter has the default value. If I had a whiteboard, I would draw it. I was assuming I'd be in a room with a whiteboard actually for this class today, so I thought I was going to draw some stuff, but we'll make do. And finally, this is also something that's in C++, but a lot of other languages don't have this. We have this notion of overloading. So we can have two functions that have the same name, but take different numbers or types of arguments. So again, C doesn't have it. A lot of other languages choose not to have this, but in C++ we do, and it's a very powerful technique. It can be overused sometimes. So when we call a function, the compiler will look at all the functions with that name and try and decide which one is the best, which one best matches the argument types that you're given it. It's a process called overload resolution. It can be a bit complicated sometimes, but most of the time you'll know which one you're trying to call.
If you overload, but you don't, and you provide a default,
Yes.
you do, and you leave the default out of the call.
No. So if you've got...
You can. You're asking.
Oh, sorry, yeah, if you can omit the
Yeah, I mean, if
The defaulted
if you have an overloaded function,
yes.
and then but you also have default parameters in the function.
Yeah.
You don't call the default. If you call the function,
Yeah.
does it go to the one with the default in?
So you can't declare a function that takes the same parameters twice, and one of them has a default and one doesn't. That's not a valid overload. A valid overload must either have a different number of parameters or the same number, but one of the types or more is different. So if you did that, you're literally just redeclaring the same one, and you can't actually do that.
Okay.
But yeah, so say you had a default, let's say the last parameter is an int, like int I equals 5, then obviously no, you don't have to provide it, but you can have something else that's a different overload that doesn't provide a default, providing something's different along there, but that's then considered a totally separate overload, and the default of the other one doesn't apply to it at all.
Yeah. So.
Question is?
When you talk about overloading, do you mean that you call several times? You can call several times a function with different argument, right? Not like you declare a new function, two functions with the same name.
No, the second one.
It has different things in the body.
It's the second one. So yeah, overloading means you can have a function called func that takes an int, and you can have a separate function that's also called func that takes a double. And those are two different functions. And then when you call the function, depending on what type of argument you pass to it, it determines which of those two functions is called. Again, I'm pointing to the wall as if I had written these things down. It would be really handy to have a whiteboard.
So what is inside the body can change.
Yes.
That's right.
These two functions can have completely different bodies, function bodies. They're two completely separate functions.
So basically
Sorry.
thank you. So basically the compiler, it will try to get the more appropriate function, taking as a reference the type the function gets as an argument.
That's precisely it, yes, absolutely, 100%.
Is that useful or related in any way to polymorphism? I was asked about polymorphism in a phone interview the other day, completely flunked it, so I'm not really reading about it.
So polymorphism and virtual functions is to do with function overriding rather than overloading.
Okay.
So that's where you have a derived class that implements virtual functions from the base class.
Java's interfaces. So you declare an interface and you have implementations of that interface. C++, we have the same ability, we just do it in a slightly different way. You have a base class, and we use the virtual keyword on its member functions individually. So unlike Java, where you just have to have a whole class and then say this is an interface, we can actually sort of mix and match and make certain bits concrete and certain bits abstract. And then you have derived classes that they inherit from them. Your consumers will only know the base, they'll only know the virtual one, right? But you can pass them a real implementation. One of them, is a logging, for example, right? All you know is you call a log function. And then one implementation someone makes will log to a file, and then one will log to the screen. That's polymorphism.
We have a question as well from YouTube. What's the best case use for function overloading?
A concrete use case of function overloading.
No, what's the best, not concrete. What's
The best case?
Yeah.
I mean, okay, a good example is logging, actually. So I want to log some data. I can have several overloads of the log function, and now I can log strings, because I have an overload that takes a std string. I can have one that will log numbers, because it can take an int. And I can have one that will maybe take an array of strings, and that will be std vector of std string. So by having overloads, it's convenient for people using your stuff, because then they just call log every time, and you can handle quite a lot of types. That's probably a good use case for overloading, I would say. You can get fancy, of course. You can use templates in certain cases and then specialize, but that's like overloading on steroids, really.
Yeah. So, I'm really squeezed in the corner.
Do you want to move this?
So a function must be declared before we can call it. Okay, this is the thing that's kind of unique and a bit nasty in C++. It has to literally appear in the source file above where we want to call it.
So that's pretty much the case for every language, isn't it?
It's a case for C and C++. Other languages say it has to, you have to have imported from the module, or it has to be in the same module.
It's not the case with JavaScript. Right? JavaScript behaves in a little strange way with that.
I mean, in Java,
In JavaScript, you can actually call a function in a line above where you've declared it,
Yeah.
because of the way that JavaScript interprets.
Yeah.
same in Java. You can declare a function, a method at the top, and then one at the bottom. And the one at the top can call the one at the bottom. No problem.
No, it's fine.
So because of this, we typically put our function declarations in a header file. That's the bit of code, the declarations that can be reused in multiple source files, multiple implementation files. We'll put the definition in one implementation file. There are exceptions to this rule, there are exceptions to everything in C++, but this is the most common way of doing things. Oh, there's it stuck outside. Sorry? Any more questions about functions? Because, like I say, this is rapid fire revision. Nope. All right. Let's move on. Variables.
Can I ask a question? The previous slide that you mentioned about declaring function after not implementing function after declaring. Is it same as abstract method or interface method in Java? In
No.
Java you have interface, you declare interface, and then you put it, you implement interface after.
I see where you're coming from. That would be, so in C++ we'd say there were base classes that had abstract functions, and then you'd have derived classes that implement those functions.
In Java,
Yeah.
we have abstract as
So we do that in C++. We haven't covered it in the course yet, but we can do that in C++. But this is a bit different. This is just telling the compiler what is the signature of this function. What does it return? What's it called? What are its arguments?
well.
Yeah.
What's the reason we don't implement inside that declaration? Why we don't mention what is the function about even you're declaring?
Different reasons. One of the reasons is speed, not really that relevant these days, or it could be if it was a massive function. But say when your source code is compiled, right, and this is the same in Java actually, it's one file processed individually at a time. So when the compiler compiles one file, it uses the function, right? If it doesn't have to then pass all of the body of the code in the function, that's actually faster. Now it just looks at the declaration, puts in the placeholder, and the linker then links it up. So only one time you have to actually process the body of source code of the function. Another reason as well is of course hiding. You could obviously compile an object file and then someone doesn't know what's in there. Of course people can reverse engineer and stuff, it's a bit silly, but that is one argument as well. But that's why people like pointer to implementation as well. You can release a library, it's a binary, and they don't see the actual code in the class or the structure of the real class they're going to use. They have what's called a point, they have a wrapper class that instantiates a pointer to the implementation. So again, so basically for hiding, speed, that's about it.
All right, let's go on to talk about variables. What's a variable?
Just data.
Named data.
Is a way to label a data.
This is what I'll call it. Name, storage, location for some data. The important thing is every variable has a type. As we said in the very first slide, every variable has a type. That type needs to be known when you declare the variable, or deduced when you declare the variable, and it can't ever change. And the other important thing about variables in C++, if I can press the right button, is that the lifetime of the variable is tied to the scope, the block in which you declare it. So when we leave the block in which the variable is declared, that variable is destroyed. And we'll find out, probably next week actually, about how we can write functions, special functions called destructors, which get run when we destroy a variable that allow us to clean up any resources that variable is holding. And keep banging on about it. This is the way we manage memory these days in C++. Right? So we really don't want to have to do manual new and delete and taking care of exactly when we finished with a variable. We let the compiler take care of it for us using this scope-based lifetime, goes by this silly acronym RAII. Really powerful technique.
Anyone know what it stands for?
Isn't it like RA2? Or
No, it's RAII. Anybody know what RAII stands for? Resource acquisition is initialization.
Yeah, it's a silly name.
Bjarne came up. Well, Bjarne came up with it. You understand it.
Yeah.
It's just insulting the creative C++. It's fine, yes.
Well, he said it was a silly name, so anyway. Whenever we declare a variable, we should give it a default value, an initial value, right? C++ annoyingly doesn't enforce this. It lets you declare a variable with no initial value, has for fundamental types anyway, has an indeterminate initial value. And if you do anything with an indeterminate variable other than write to it, then that's very bad. So uninitialized, yeah, it has an indeterminate value. Yeah, and this is the basis of many security holes in C and C++ programs. So always initialize your variables. Always initialize your variables.
The only time you wouldn't do it is being very clever and you know you're going to write to it first thing, but you only want to write to it a bit later. So you want to save the computer having to actually go and write the memory. Problem is, if you don't do that, then this is how security exploits happen. It calls into your function, you forgot to initialize it, and you read it. That data is probably something from your stack. So say you've got software processing, data, and it's doing encryption or decryption. It just so happens that last piece of data it used was the decryption key. Now you just leave the data because it's uninitialized. It just reads it out. For example.
There are 3 ways. Well, no, there are a lot more. There are 3 main ways to initialize a variable in C++. 3 different ways of writing it. I haven't put these on the slides. This is where I was going to use the imaginary whiteboard, right? This is what I was planning on doing. There are 3 ways of doing it. Can anybody tell me, well, one of them? Curly brackets. Yes. Yeah, so we can write whiteboard, imaginary whiteboard, int I, curly bracket, and then 0, and then close curly brackets. Semicolon, yes. Curly braces, what's the second one? Equals, I don't know, I didn't catch who said that, but yes, we could write int I equals 0. In most cases.
Most types, for most types.
And the third one, what's the third one?
Complex element.
The third one, yeah, round brackets. So we can do it with curly brackets, or we can do it with round brackets. Really, really annoyingly, in most cases, the curly brackets and the round brackets do the same thing. And for a very small number of types, the curly brackets and the round brackets do different things. And when we get on to talking about vector later today, we'll see an example of that. Oh, no, that was...
a paper to fix up something else.
So recommendation for me anyway, if you for just built-in types like ints and floats and bools, I tend to use the equals form. I just find it more natural. I say int I equals 0, float f equals 3 point whatever. And then for class types, things like strings and vectors, I'll tend to use the curly brackets forms. And then I use the round brackets form when I have to. But a lot of it comes down to personal preference. Oh, I thought you were showing me something.
No, sorry. Just trying to take a photo.
So we can use the auto keyword to declare a variable. When we do this, it means that the type of that variable is deduced from the initializer. It still has a defined type, but the type of the variable is deduced from the initializer. It can save us typing out if there's a very long type name or we don't know the type name. We just write auto. Basically a way of saving some typing. Does that make sense? Excellent. Hello, Justin.
So, would you say initializing the variables is generally good practice, even in the language, or just C++?
Most other languages, I think, either require you to put some sort of initializer in there, or they give a type of sensible default value.
Yeah, like for example, Python, you don't have to initialize. Just
No, but somebody who knows Python a bit better can correct me, but I think Python, if you just, how would you do it?
just say something is equal to whatever.
Yeah.
It will automatically find it. But it's just the question is whether the security bugs is it all still like if you write a program in Python, are you then able to still sort of manipulate the program if you find security bugs because you didn't initialize it variable?
Not quite.
I don't think so.
Different nature of exploits.
Yeah. I don't think
It's further abstract. It's more abstracted from the hardware.
I'm not sure you can have an uninitialized variable in Python because it's a bit like with auto. You can't omit the initializer from auto.
because there's no keyword.
Yeah,
You don't
because
need
otherwise
keywords.
the computer won't know what type that variable is.
Question from
Yeah.
the internet. Is there a good reason why we have different approaches to initialization?
A good reason. The curly brace bit was added in, or for most types was added in C++11 so the equals form and sometimes the curly brace form came from C, so we needed them for backwards compatibility. The round brackets form came because we were calling these functions called constructors, so they were function calls, so you made them look like function calls. And then in C++11 they tried to make this all uniform. They even called it uniform initialization syntax, so that you could use curly braces everywhere. Only it didn't quite go according to plan because there are still cases where you have to use the round brackets.
And you go over const and const x, or are you
I wasn't going to talk about const actually. So yes, we can declare a variable as. Sorry.
just while we're on the
Yeah, we can declare a variable as const. When we declare a variable as const, it means we can never change its value after we've initialized it. It's a read-only variable. And actually, if we declare something const, the compiler will make sure that we give it an initial value. Because if you think about it, if you don't give it an initial value and you can never change it, what's the point of it, right? So a really good approach is to declare your variables as const by default, and then only remove the const later if you. Something amusing, but I don't know what. Only remove the const later if you find that you do actually need to mutate that variable. So const, it can, and Jacob's going to get annoyed with me again. It can, in some cases, lead to better optimization, but also, more importantly than that, it stops you making mistakes. So make things const whenever you can. Const extra is a sort of stronger form of const. const expr variables have their initialization computed at compile time, so when the compiler runs. And you can have const expr functions that can be executed at compile time. And there are all sorts of restrictions about what you can do in const expr functions. So const expr is mostly about making things more efficient. So execute functions and then have the result of that function like baked into your executable rather than computing it when the program runs.
So why are they different? If the const expr and const are doing basically the same thing, why there are two things?
Okay,
Why
so
isn't the const
you can imagine that you get the user to input something, to input a string. Say, what is your name? And they say, in my case, they'll say Tristan. And then you can save that into a const string because they assume the username is never going to change over the course of the program, right? But you can't do that at compile time because that depends on what the user tells you. But if you had another string that said, what operating system is this? Well, you only compile for one operating system at a time. So you could have the operating system name as a compile time string. And then it would be baked into your executable. You wouldn't have to initialize that variable at runtime.
So using your example, so you have something called a const string name, your username.
Yeah.
And then you say, in string, what is your name? And then you get that variable into username,
Yeah.
right? So that username will get Tristan.
Yeah.
And because it is const, it will never change.
You can never change it after initialization, correct?
But what is the original value before I actually, so when I say const, string, username, semicolon, what does it actually initialize?
Well, in that case, because of the way that the iString functions work in C++, you'd actually have to do it, you'd have to have a function that had a temporary string, read into that string, return the string, and then assign const standard string username equals get username. You can't do it in one step in C++, unfortunately. Right.
No questions?
No questions.
No questions.
Let's move on. References. You know what the first question is going to be? What's a reference?
Alias.
An alias. Yeah. It's a new name for an existing variable. Right? We're declaring a variable, a reference variable that refers to some existing variable. You cannot have an uninitialized variable. Kind of an uninitialized reference, sorry. Kind of a reference that points to nothing. So we declare a reference type by putting an ampersand, an and symbol after the type name. So for example, you'd write imaginary whiteboard, int and you have to give it the name of an existing variable. We can think, as I said, we can think of it as a new name, an alias, if you like, although strictly speaking, the word alias means something else, but that's an alias is we have type aliases in C++, but yeah. So most often references are used to pass parameters by reference to functions. So if you recall, C++ passes by value by default. So pretty much one of the most useful things you can do with references is to pass by reference to functions. And this means that the function will operate on not a copy of the argument, but on the actual bit of memory where the original variable lives. So again, good rule of thumb, use const, type, and, could be int, float, string, whatever it is. Use const type most of the time to prevent copying. And on rare occasions, when you actually do need to mutate the arguments, if you have what are called in-out arguments or in-out parameters, out parameters, then you can leave off this const.
So when you declare a variable, for example, using this ampersand or and, then if I change, for example, say this new variable, new underscore variable, if I change that new underscore variable, is that going to change the original variable?
Yes, yes, it will. That's the whole idea behind references is that they're both names for the same bit of underlying memory.
So then, what's the value of that? I mean, is it like an example where, for example, like if I use, because usually if I want to make a copy, it's because I want to use that copy and don't want to affect
Yes.
the original one.
So there's very little point in having a reference in the same scope, right? Having a reference to the same variable in the same scope. I used it in a couple of examples when we first did references.
Same function is another way of thinking.
In the same function. But as I say, where it is most useful is as a function parameter. So you could have a function that takes int ref, int and then if you were to assign to that parameter inside the function, what you are changing is the actual value of the argument that's passed to it. Yeah.
Why the east cons is better than west cons?
Shut up.
Does that improve the memory? Is it more memory efficient that we're using references and parameters?
Yes. So let's say you had a big vector that had 10 million things in it. If you pass that by value to a function, it's going to copy that vector. It's going to assign a new 10 million, whatever that is, 10 megabyte, 40 megabyte vector, just to operate on it and then throw the data away. Whereas if you pass it by reference, and especially by const reference, it doesn't have to do the copy.
Same is not true of tiny trivial things like int, double, float. Anything that's guaranteed small and trivial is probably better to copy it. Taking like an int ref might actually not necessarily be good if the compiler can't see that it's not modified, whereas it always knows if it's just taking a copy past the register, for example. That's strict optimization stuff. That's way in the future. Don't worry about that right now. And there's a question in the back.
Yeah, I was wondering the in-out example you had of where you would copy a reference into a function or into a scope.
Yeah.
Well, where would you use that? I just can't think of a good example where you would use that, where you need to do that.
Use what?
Why would you use a mutable reference parameter to a function? As opposed to?
As opposed to
how about a concat function? So you have a function that takes a std string ref, and then it takes const string ref, and it just takes your existing string, finds something on the end.
Okay, so imagine you had a function called make uppercase, right? Yeah. So you have a string that's got mixed case, and you have a function make uppercase that takes that string and it changes all the lowercase functions to all the lowercase letters to uppercase letters, right? There are two ways of writing that. Either you take a copy of the string, operate on the copy, and return that copy. So now you've passed in the mixed case string, it's been copied, we've modified the copy, we've returned the copy. So now we've got two strings, the original and the modified one.
Yeah.
A more efficient way of doing that would be to pass the original string in as a reference, because then we don't have to allocate a new string on the heap, we don't have to do any copies, we can just go through that original string and change every lowercase letter to an uppercase letter.
Yeah.
So it modifies the existing one in place.
Yeah, but I was thinking in the use cases where you wouldn't make that a const.
So in that case, if we were modifying the thing that we pass in,
yeah.
It cannot be a const reference, it has to be a non-const reference.
Oh, yeah.
Yeah.
Yeah, I think so. Yeah, I'll try it.
When does the const reference make sense to use then in that case?
Whenever you don't need to modify the value that you're passing.
You just need to read from the original value.
Exactly that.
Then it's
So if so
it's
now
really big, you don't want to copy it.
Yeah.
It's insurance, isn't it? Against
Exactly that, yeah. So we could have a function called count A's, which counts the number of letter A's in a string. Now we don't need to modify the string for that. So we could pass it by const reference, we can just iterate through the string, look, compare every time we get a letter A, and in that case we could take a const string reference. Yes, yeah. Just the first example off the top of my head. So that's references. Haven't got too many more of these, don't worry. Pointers. We had some fun. So the last time I was here, which is now 3 weeks ago, back over there somewhere, I ran through pointers in 15 minutes. But fortunately, while I was away, you had Ollie who did it in much more detail.
Can I ask,
Oh.
one question from the internet. Type safety is already established by the declaration, right?
Yes.
Yes?
By the declaration of the function.
Yes.
Yeah.
Well, it's established by the language itself.
Yeah. So
Type safety is a functional feature of the language itself. It's not something you as a person make happen. It's just like the language's syntax and semantics. If you couldn't hear it, tell me if you couldn't hear it and I'll type it for you.
Thank you.
right, what's a pointer?
That's the thing of the answer.
Laser pointer.
It's a memory address. Yeah, it's a value, a variable. It's a value type that holds a memory address. So you can think of, we did all these analogies before, we can think of it sort of roughly like a file name. Right? If you imagine your variables are like files on your computer, a pointer is like the name of that file, where it lives in memory. And we declare a pointer by saying type star, so that could be int star or float star or standard string star. The little star after the type means pointer to this thing. But in order to meaningfully instantiate these things, we have to be able to give it the address of a variable. And we take the address of a variable by putting an ampersand in front of its name. So this is a bit confusing with the ampersand because it has two meanings. If we put it after a type, it means reference. If we put it before a variable name, it means address of that variable.
Can you say everything to the left-hand side is a reference, the left-hand side of an equal sign is a reference, and everything to the right-hand side of an equal sign is a point, or is it the address?
Sorry, you got that? Run that by me again.
Can you say, this is what I was just wondering, can you say everything to the left-hand side
Of an assignment?
of an assignment or equal sign
Yeah, so
is a reference when you see the ampersand?
that's beyond
Oh,
time.
I see.
Everything to the right-hand, everything to the other side, right-hand side, is related to the address of.
Yeah, so if you see and
Because I get
and
so
very-
confused, I see ampersands everywhere.
yeah, it's actually
Is that something to hold in your mind? Is that something you can hold in your mind?
It's probably better to look at what the and is attached to. So if it's attached to a type name, it means reference. If it's attached to the front of a variable name, it means address of. It's probably a better way of thinking about
Or
it.
it follows a type name, because someone could put a space.
Yeah, well, that's the problem, because you have it,
Yeah.
you can have them all over the place, can't you? Because they're not syntactically together. They don't have to be syntactically.
You could type like int space star space name,
Yeah.
or you could do int star space name, or you could do int space star name.
It's actually a good
Look to the
example
right.
of why we
Look to the
need.
left, look to the left.
I was just looking for rules.
It's an actually good example of why we need declarations in C++ before we get to before we use a name. Because if you just in a function, if you just saw the line A space star space B, there are two possible meanings for that. Either A and B are variables and we're trying to multiply them, or A is a type name and we're trying to declare B as a pointer to A. So that's why we need to declare things ahead of time, so the compiler knows when it gets to that line, it knows what type, what A and B represents, what kind of word is identified, what kind of identifier they have. If you don't want to litter your code with these things, there's a function called standard address of that does what this does. So you can make things, it's address of, all one word, for some reason it doesn't have the underscore in the middle that you'd expect. And it can make things, it can make it a bit more clear when exactly you're. So I tend to use address of all the time. It also.
It may also break things, technically speaking.
Address of?
Yeah, because obviously that goes to pass the overloaded operator ampersand.
Yeah, which is always a good thing.
Oh, that's not necessarily true.
Never overload the address of operating
No,
as
you
well.
should never do it, but if you're working with something that relies on it.
Always initialize variables. Might have mentioned this before, can't remember. So there's this special pointer value, null pointer, null putter. It means no value, right? It's where if you don't have something for your pointer to point to, there's no valid int for your int star to point to, then initialize it to null pointer.
Don't dereference it.
And we can dereference a pointer by writing star name, which returns a reference to the pointer to variable. So if we have an int star points to some, which holds a memory address of some other int over here, and we write star p to dereference our pointer, that's going to give us the value of our other thing, the reference, the pointee, the pointed to variable. And as I just said, dereferencing an invalid pointer is undefined behavior. Undefined behavior is what the C++ standard says when it says absolutely anything can happen. So the famous thing is demons could fly out of your nose, right? It could format your hard drive. It could eat all the cheese in your house. Anything can happen.
Probably just crash.
Yeah.
Probably just crash horribly. But
Yeah.
there's rare cases where it doesn't, and then you'll never know for a week or two, and then it will suddenly surface, and you'll be really, really angry.
Or even worse than that, it appears to work correctly, but then some hacker uses this as an exploit. So, what?
Do you avoid that?
How do you avoid that?
Don't do it.
Firstly, you've got to be. Firstly, with pointers, it's quite easy to get into a situation where you're pointing to a variable that has either been deleted or gone out of scope, or in any way is not there anymore. And then when you try and dereference this pointer to something that's been deleted, with use after free, then that's this last case, and that's bad.
What's the difference between null, capital N-U-L-L,
Yeah.
and null pointer, no PTR?
So null, capital N-U-L-L, is a macro from C, an older C++. Null pointer is a keyword built into the language that is in some ways a bit safer than using null.
Has its own type. Null pointer has its own type. In fact, you can declare a function that takes null pointer t, and then you can only call that overload with literally the word null pointer. Whereas null, all caps, is just a macro, and it resolves to literally the same as typing 0 on your keyboard. It's just the number 0, which is bad because if you have an overload that say takes a char star for a string, and you have one that takes an int, and you use null, which one's it going to go to? Whereas if you use null pointer, it knows that it goes to char star. Obviously.
Do you have a question?
Yes. You mentioned that life of variable is in the block.
Yeah.
What about pointer and reference? The life was in the block they are there, or after that?
The life of the pointer itself is exactly the same. So a pointer is just a value. So when you leave the block that the pointer was declared in, that pointer goes away. But the thing it was pointing to may live on.
And we have to delete it manually, or
Nowadays, no you don't. Once upon a time, yes, you had to worry about that. These days we have these things called smart pointers that take care of that automatically for you.
what about reference to the block again as well?
Again, the reference is only exists for the scope E declarative, block E declarative.
Well, the lifetime of the reference is separate from the lifetime of the object it's referencing.
Yes.
And the same for a pointer. The lifetime of the pointer is separate from the lifetime of the thing it's pointing to. Because I can make a pointer point to something else, right? And it's not going to destroy the thing it was pointing to. Smart pointers can do that for you, though, but raw pointers, no. They don't have a fixed lifetime.
I just want to make sure I understand this. If it's int star and then space and name to declare the pointer to the address of name.
No, that declares a pointer, and the name of that pointer would be name.
Okay. And then when you say dereference a pointer,
Yeah.
what do you mean the reference to a pointed to variable? So like you return the reference of and boolean.
Okay, so let's imagine we declare int I equals 3. It's flipping whiteboard. Right, int I equals 3, and then under that we do int star p equals address of I. Right, so we've initialized I as an int, its value is 3, and we've initialized p as a pointer whose value is the memory address of I. Yeah? And then later on, somewhere down there, we do star p equals 4. And that says dereference p, so get a reference to the thing that p was pointing at, and change its value to 4.
So it's going to change I to 4.
It's going to change I to 4. It's much easier. All right, that was pointers. This is our rapid fire revision, right? Which has actually been going a bit longer than I expected, but never mind. It's all good. I think there's that question. You're just scratching your head. This is the last one. Let's talk about loops. 4 different kinds of loops. I'm going to run through them. We've got a bullet point for each one. A while loop. I'm just going to go over them quickly because this is familiar stuff from most other programming languages. So a while loop, say while brackets condition, and then have the body, and it keeps doing that until the condition is false. But importantly, it checks the condition first. A do while loop is the same, except it runs the loop first, then checks the condition. So a do while loop always runs at least once. A while loop, if it gets to the condition and the condition is false, it never executes the body. Do while, it always executes the body first, then checks the condition to see whether it should go again. A for loop with three element for loop is basically like a while loop with a bit of nicer syntax, because we can declare, usually use the first of the 3 blocks to declare a variable, our loop counter, then we have the exit condition in the middle, and then we have the increment condition. So you might do for int I equals 0, I less than 10, I++, which will execute the loop 10 times and then exit. And then lastly, the fancy new thing, we have this range for loop, and this runs the loop for every element in a container, a compatible container. So all the standard library containers implement this range protocol, if you like. So you can use them in a range for loop. So that's nice, handy sort of syntactic sugar. So a range for loop is a handy way of writing an ordinary for loop, and an ordinary for loop is a handy way of writing a while loop. And we can break out of the loop at any time using the break keyword. And if we want to jump back to the start of the loop and test the exit condition again, we use a continue keyword. Just jump back. That should be jump. I don't know why it says just. I'll edit that now because I'll forget to do it in the slides otherwise.
Is using break good practice?
Yeah, if you know that you're done with the loop and you don't have any more use. So what you can do in particular is have sorry? If function. Oh yeah, so you can have like infinite loops. So you just do while true, and you just keep on testing this condition. But then if some complex thing is true, then you would call break to leave the infinite loop.
There are also cases where it's probably a bad idea. Break is just a keyword. It's one of those ones where there are ways to design a loop that is horribly unreadable. Break can add to it. If you've got tons and tons of conditionals where they can all break, probably horrible. And then this case where it makes perfect sense because it's the only break statement in the loop. So it's just one of those things that comes down to style and how you architect your code.
Right, that's the end of the revision material.
Questions before we break into the
Yeah.
test?
I know in Java you can
Sorry.
I know in Java you can put the label and then put the continue going back to label. Is it? Do you have labels in C++?
Yes, there are labels and there's go to.
Oh.
The keyword is go to, and you can go to jump to a label, and that label can be up. It has to be in the same function. It can be above. It can be below. Yeah, you can say go to this label. It's generally considered quite bad style to use go to. Right? There's a famous from the 1960s, I think, paper called "Go to Considered Harmful." Right, so generally avoid go to, but it is technically possible to do.
When do you use, or is it a good practice to use const cast?
Oh.
Very, very rarely. In fact, all of the casts. So, a cast is a way of punching a hole in the type system, right? Of saying, I know better than you, compiler, right? So we're going back to our example of file types. It's like forcibly changing the extension of a file on Windows so that you try and get Word to interpret this PDF as if it was a Word document. Right? That's what you're doing with a cast. You are saying, I know this is an int, but I want you to pretend that these bytes represent a float. And what const cast in particular lets you do is add or remove const. CD qualifiers, technically. You can do the same with volatile. Removing, it's almost useless const cast because if the variable was declared const in the first place, then using const cast to remove that const is undefined behavior. It breaks your program. And there's no point using const cast to add const because you can always declare a const reference to an const thing. So I cannot think of any legitimate use for const cast that isn't just trying to save yourself a few lines of typing. That's really the only reason I see it come up. Maybe Jacob has a good use for it.
Yeah, interactive with C APIs because in C,
right.
yeah, you don't have a const star. So if you want to push something that you know that function directly won't modify the value, then you need to take your C++ function a const string or wherever, const cast it, and then push into your C API because there is no other way.
Yes.
There's not a lot of
Yeah.
Otherwise, in your own code, you should never cast. Basically.
Basically, yeah. Especially heavy use of casts is a sign that there's probably a sort of design issue with your code. But as Jacob said, there's a very good example of it. Yeah, particularly C code, where the const keyword isn't used nearly as much as it is in C++. So you might have to cast away your const just to be able to call C functions. There are some cases where you have to use, or you don't have to, but you can use one of the casts, a static cast, to do things like moving variables, but we tend to wrap those in functions to make them look a bit nicer.
I have another question.
Yeah.
We studied pointers primarily from the example of char string or char array, whatever you call it. Char array is also, in essence, a string in C++. So, I guess my question is, just for the study of pointers, I can see why you want to do the char stuff, but is it always a good practice to use the built-in object instead of
Okay, so when you write a string literal, for those of you who don't, when you write a string literal, that's a bunch of characters in double quotes.
A C string is it's also, yeah.
The type of that is array of char, array of characters. That's a raw language array. And if you remember, I covered this in one bullet point that said raw arrays are horrible and don't use them. And the reason raw arrays are horrible is because they convert to a pointer very, very rarely. Right? There's this automatic conversion from C from an array to pointer conversion is what it's called. right? Hey, yeah. And that makes them really awkward to work with. So what you'll very often see is that a string literal is treated as const char star, pointer to a const character. Well, it's actually a pointer to the first in an array of const characters. And that's a legacy that we have to deal with from C. It's unfortunate. If you can, use standard string, because it behaves much more regularly. It's much easier to use. Rules around it are easy to use. In C++ 17, there's something called string view. So a standard string allocates, and the heap probably has a short string optimization, but it allocates. A string view is what we can use for compile time strings. It never allocates any memory. It just provides you with a nice C++-ish interface around the string. So we're not doing C++ 17 in this course yet. When we do, I'll start using string view everywhere. But yes, unfortunately, we have this legacy where string literals have type const chart star, which is unfortunate, but it's one of those things that we have to live with, unfortunately. So that you'll see that an awful lot in examples. I'm not sure whether I answered the question or not because I got completely distracted talking about C arrays.
So basically, what I deduce from the answer is if I could control it,
Yes,
don't use the string literals.
precisely.
Use strings whenever possible.
Yes.
But I have no choice because of the legacy that's left over. Then
Yes.
I have to understand why this is a const star.
You potentially do have a choice. So if it's taking a const char, if it's say a C library taking a const char star, then you can still use string because you can use the .c underscore str overload, which will give you back a const char star, so you can still benefit from std string. Where it gets more annoying is when it's C functions that want to mutate a char array, so they want a char star. Currently, std string will not give you back a char star, but if we have .data that is
17.
useful, yeah, so it's relaxed it more since 17. There's now a member function on string that will let you mutate its bytes, but the problem is you can't change the length. So you can now call C functions, and as long as it doesn't try and change the length, it just modifies in place, that's okay. So we now have that power as well since 17. Okay.
This is the last chance. Any more questions?
It's not that long. It's not that long of a quiz. It's just a quiz. Don't freak out.
Yeah. Right. Yeah, laptops away. No textbook. No.
No, it requires laptops on there.
It is a test. It's not a test. It's a quiz.
How long is it?
Depends how experienced you are.
Take time. Don't rush.
I've pasted it into the Slack channel if anyone wants to just click and not have to type it out.
If you go to this URL, you will see a bunch of questions. Make sure you put your email address at the bottom. Otherwise, we won't get your results. You won't get your results. Is that right? We'll
Sorry?
have to change that.
Yeah, please enter your email. We won't know who you are.
Yes.
I'll just have anonymous test results and nobody to link them to.
Then you can
It's for you, not for us. I mean, it's kind of for us to see how you do it, but it's really for you.
Gives us a good indication of whether we've got things right in terms of
Are we too fast, too slow?
exactly.
Coffee? Read down there. Back. Thank you. Here you go.
Well, you can go to the Slack channel.
Yeah, just go to our Slack channel. I pasted it there for you. Downstairs.
Let me copy the Slack, the URL to the Slack channel.
No.
I email. I haven't posted it for the license. I haven't
No.
I don't have licenses yet.
Oh,
I'm still waiting.
okay.
I'm waiting for.
But you could give my email to students and
I think that you are the only person which is left without a license.
Oh, yeah, yeah,
Unfortunately, you were a little bit
yeah, I was
delayed.
you can just asking if you like to.
As soon as I have it, yeah, I'm just waiting for Phil to come back to me.
When it's equal to
I've just got a question here. Sorry,
That's B7JBJM5.
that was fine. I thought that just wasn't a sentence.
Unfortunately, the last time we were in this room, the background music came through on the thing, and YouTube yanked the our video.
No, that was in the common area.
Oh right.
Yeah.
Oh, okay.
Harvard is a traitor.
He did look in, but
So with the Rust guys.
He wanted to get in. There was no space.
He's with the Rust guys.
should just be able to put.
No, I'll paste the link in YouTube by the way, Tom.
Sorry?
I tried to paste the link in YouTube.
No? I'm just pasting it. Yeah, it doesn't. It looks like Google doesn't like the idea of us.
Oh, we've got a few come in so far. Yeah, absolutely. If somebody gets ordered right on if they want to. Takes forever. Or Tom, I don't know. We've got someone who's got 100%. Justin. Got one wrong, man.
I've switched 2 minutes ago. Shouldn't be switched.
What about Alex? You submitted, right?
Yeah, I submitted it.
One wrong.
Oh, that really frustrated me, that one.
The last one.
Yeah,
It was only the last one I got wrong.
to be honest, the one with the checkboxes, I pretty much guessed with the wording. I really wasn't sure about that one.
Oh,
Argentina are winning 1-0 if anybody cares.
Against?
Nigeria.
-1.
Winning 1-0 against Nigeria.
Any predictions for the finals?
My mate swears down that Croatia's going to win.
Yeah, Croatia's doing really well. So is Belgium.
Haven't got the biggest win so far, though, have they?
Who, England?
Or Croatia or Belgium?
Croatia, yeah.
Sorry, we've got a few days of being smug before it all goes wrong for England fans. So.
So in this group, which one will be the top two?
Russia's also.
Argentina's group.
Sorry? In Argentina's group, I don't know.
There's Iceland, Argentina,
Iceland, Croatia is 0-0 at the moment.
Croatia and Nigeria actually on top in the Argentina's group. So even if they won, do they get 2 points or 3 points?
3 points for a win.
It's
France against Argentina.
Okay. At the moment, Croatia and Argentina are going through from that group. Because he knew Argentina would scrape through, despite having struggled so far. Anyway, sorry. Yeah, we'll let other people concentrate rather than talking about football.
Just put it. I got 15 completed so far. Oh, you just ran the code on the last question? Oh, I know what's going to happen now. Disqualified for cheating.
I can say use any resources you like.
Plus, this is your fault, I get to blame you.
Use any resources you like. Just ask Justin.
Oh, yeah, Justin, you can't help it.
Oh, just to either, if your name's on the list, just tick to say you're here, or if you're losing, just write the name.
It's just our register.
Just so we know how many people we're getting to the classes.
But if you register as a meter, you have to do the same as well on Skills Matter.
You do, yeah.
Always, you have
So when we're at Skills Matter, they collect their own separate stuff, which is terrible for us. You can't get in touch with people. And sometimes we're not here. So
you have to do it on course here.
Only when we're here. So some weeks we're not actually here. We're elsewhere. Like usually will be where I work, which is just up the street. But then obviously you don't register with Skills Matter. We keep the register of names so we can let people know.
How many you've done?
I got one more.
One set.
Yeah.
Which one? Last one.
Oh, what are you going to say? It's fine.
You always have concerns.
Yeah. I mean, we usually go here because it's a lot less stress for me to have to do a better organisation around it. So when we've got it. But if I'd have known we wanted to be stuck in here, I would have got something there.
Yeah.
91 responses. Very actually. Well, this one's pretty big on. Has everyone done it?
Is anybody still working? Needs some more time? Put your hand up if you need more time.
Sounds like nobody. No?
Nobody with a hand up. Okay. Do you want to switch over? Sorry?
Yeah, go on.
Oh, hang on. I'll stop the stream on this one. Really?
Yeah.
But we've done this before where we just stopped for a minute. It worked. So if Ollie starts streaming in just a second.
I mean, at the beginning, that created a separate file.
I mean, you can always just go to that. Stopping.
We'll have to piece these together. Alright, ready? Not ready. Okay, right. So we're going to go through the results then. I'll see a few if you got 100%. We can go through individual. If anyone wants to go through their individual results as well, we can do that. So most of you obviously got this one correct. I've actually got the analytics as well, right there. So let's see. First, yeah, question 7 is the one that tripped most people up. But so most of you said it was obviously stood see out hello world, and you of course were correct. So I'll take you through the set. Go on. Yeah, let me sit actually, it's easier. So just so you can see what it looked like on the actual one, that was the correct answer. Number 2 was obviously select which statement is factually correct. I don't think anyone got this wrong, but let's have a look at the aggregated data. Nobody got that wrong. All 22 of you correctly said that it was that one. While loops, of course, have a single expression and they add up to 3 for a for loop. And then the correct answer, of course, which one's factually incorrect. So, of course, it was a function returning void star does not return anything because, of course, it's returning a pointer to void, which is something. Void is nothing, so that one's true. So this is the only one that's actually false. Let's see how people did with that one. So, yeah, we tricked a few of you up. But the majority of you, again, you got it right, so I'm happy with that. That's good. And then on number 4, of course, the correct order in which it compiles is first you get the source code, that's passed to the preprocessor, which pre-processes it. That is then compiled. That results in intermediate output. That then goes to the linker, which then puts it all together into your final output file. And so let's see how that worked out. Yeah, again, 58% of you said it was the correct answer. So then question number 5 was, of course, what is true about this piece of code. And of course, it's not a reference. This S2 is not a reference. S2 is not a pointer. Of
course, it's a copy. And overwhelmingly, everybody correctly said it was a copy. Excellent. Then on to number 6. So this obviously was a little bit more tricky because there were 3 wrong answers. Unfortunately, in SurveyMonkey, it doesn't allow me to count these as being like bad answers. So if you just tick everything, you still get 3 points. But that's okay. I have ways to massage that data later. But so let's have a look through. I'm not sure how useful these will be actually because they're aggregated. So yeah, I mean, obviously a lot of people got the correct ones. These are the 3 correct ones, and a few of you actually mistakenly chose the wrong ones. And then, of course, we have what will happen in this piece of code. So, of course, it will run, but its behavior is undefined. And then for bonus points, you could say, I have to manually review it. For some reason, can I make that display if I drag it? It was displaying for a second. No? Okay, so I'll just say it. So basically the principle is that you call getString, creates a string local to the function, it returns a pointer to it, but then when you get out of it, that object has been destroyed, so this is now a pointer to something that was destroyed. You then try to dereference it, anything can happen, it will probably just crash, of course. And then this is the doozy that got most of you, but as you can see, some of you did get it right, but the majority of you were tricked by it and believed it would actually run and say hello. So I think we'll use that as a piece of feedback and try and teach you some of the more nuanced ways you can be tripped up by C++.
It's definitely tricky, that last one.
Yeah.
We threw in auto, so it wasn't necessarily obvious that you were capturing a pointer from the function.
Yeah. So that was
the fact
it.
that you asked me for why kind of gave it away there. It wasn't, even though I chose wrong answer, but like I kind of felt like it must be one of the other ones because you're like asking for why. So
yeah, why does it work is not a question that people often ask.
Yeah.
What's the difference between the 2, 1 and the...
These?
Yeah, what's the difference between these 2?
So there's what's called undefined behavior means anything can happen. You know, this program is not valid. And there's also what's called implementation defined behavior. So in the sort of language of the standard, an implementation means a C++ compiler. So you can have implementation defined behavior means this is valid, this is okay to say, but exactly what happens depends on your particular compiler that you're using. So, for example, the number of arguments you can pass to a function is implementation defined. It's usually a much bigger number than you would ever want to use, and I'm talking about 16,000. But technically, it's an implementation defined number of arguments.
And that was it.
One more question.
Yeah.
You mentioned that S, because it's the class in the block, then there is no value required to S. Did you mention that?
Yeah.
Which one?
So,
The last one.
Oh, the last one.
To make it bigger, maybe.
What was the reason you mentioned?
okay, so what happens is the program begins in main, and then it sees this declaration S, and it says, okay, well I don't know what the type of that is yet, so I need to run this function called getString. So it jumps up here, and then it creates a local variable, standard string S, and it initializes that with hi. And then it returns and S, the address of our local variable.
Which is then destroyed.
And then when we leave the function, because we've got a return statement, it destroys the local variable S. So S no longer exists.
Out of scope.
Yeah. But now we're returning the address, the memory address of something that is no longer exists. So that's what's called a dangling pointer. This is a common error when we're doing pointers. It's one of the reasons we generally prefer to use references rather than pointers. Although actually in this case we could get the same problem with references. So we've So this function getString returns a standard string star, a pointer to a standard string. And we're returning the address of a local variable. That's a mistake. So now we come back down here, and we've got another S now, and we're initializing it with the return value of this, which is, so this is going to be a standard string star, which is initialized with the address of something that's gone out of scope. So when we now called star S here to dereference S, we're going to have a problem because we're trying to dereference something that is no longer there to look at. Boom. Except not boom, because
It might randomly work.
it may work. Annoyingly, if you try this, it may work or may appear to work, which is actually one of the problems with what's called undefined behavior. Is that sometimes the undefined behavior is exactly what you expect it to do, which can make it a real problem to discover it sometimes.
So to explain why it might happen is that string will probably allocate this on the heap, which means that it asks the OS for some memory to store it in. Generally these days you have what's called small size optimization, so implementations probably will actually be able to skip that. But in the naive implementation, it asks the OS, give me some memory. It puts the high in there. Then it destroys it, and when you destroy the string, that's just internally saying, here you go, tells the OS you can have this memory back, right? Linux, Windows, here you go, I'm done with this memory. But then when you try to use it, when you tell the OS, you tell Linux or Windows that you're done with some memory, it doesn't necessarily just go and take it away from you straight away. It might leave it there until it decides it needs it. So randomly you might run it and it just runs and it seems okay. And then sometimes the OS will actually want it and take it back, and then you'll just crash because it took it back. So that's an example of why it's undefined behavior. Anything could happen because the OS will do what it wants to do. Yeah, there we go. I'll let you take back over.
All right. Musical laptops again.
Yeah, musical laptops. I should stop the stream as well. Yeah, no worries.
Yay, right. Can you tell us if that's back on, Tom?
I think it is.
Yeah, looks like it. Okay. Let's talk about standard vector. Well, in fact, let's talk about containers in general first. So the standard library comes with a whole bunch of containers of different types. There are about a dozen of them. A few of those are what are called sequence containers. So standard vector is one. There's array. There's list. There's set. There's quite a few of them. And all of these hold elements of a certain type. They're a collection of elements. And the type of those elements is called the value type.
Like array?
Exactly like an array, yes.
So why doesn't call them array?
Because you could you could have a linked list, which is not an array. And it's a different kind of data structure.
Maybe a better way to think of it is that we have raw arrays in C already, so obviously C++ comes from C, and array is already a term, and an array is strictly a fixed size container, which vector is not. Vector behaves much like an array, but it's dynamically sized.
That's the only difference?
It can grow and shrink. Is there any difference? It's got some type safety to it. Go on, you take it.
Yeah, so there is a type called standard array. So a standard array is a fixed size. You declare how many elements it's got right up front. It stores its elements on the stack rather than the heap, so it doesn't use the free store at all. Generally, an array is appropriate for a sort of limited subset of cases where you could use a vector. Vector is a more general type. So,
Just while you're there, can you clarify to our modules that what is the general rule of thumb to find these things on either on a heap or on a stack? When I see something, how can I guess whether it's allocated on a heap or on a stack?
this is a whole session by itself. So I can only touch the surface now.
So the containers are always on the stack?
No. So when you declare a local variable, you say int I equals 4. That's stack allocated. Okay, and when you declare C array of ints, those are on the stack. Now there is a way of requesting some memory from the free store. So you just go to the operating system, you say, can I have 100 bytes in which to store some ints? And you do that in C++ by using the keyword new. And then later on, you have to correspondingly call delete. Now, getting that right is really difficult. So we have these types, like smart pointers and like standard vector, that look after this for you. So a standard vector, you allocate it on the stack, but then behind the scenes, it's managing a dynamic allocation, a heap allocation for you. So it looks like, it has a small amount of stack space, typically for a vector 3 pointers worth, and it manages some other heap allocation behind the scenes.
So it's actually both.
It's both, yes.
Is that the same as all container types? Standard like
All except standard array. Standard array is a bit of a special one that is just on the stack. All of the others do this thing of, yes, you have a small stack allocated handle. It's a handle for a heap, dynamically allocated. And that's a good thing because your stack space in your program is very limited. It's probably only a couple of megabytes. It's a valuable resource. If you exhaust your heap, your program gets terminated by the OS there. Right, so you have to be very careful with that. So if you use recursive functions, you can run out of stack space, for example. Whereas the amount of heap memory you can request is pretty much limited by the RAM in your system. It's not even limited by that sometimes. So this is a really, really powerful pattern. This is like the core of C++ these days. So as I say, there are many containers, but vector is 95% of the time, perhaps more than that. If you're looking for a sequence container, so by that I mean something that's not a map, not a map or a hash table or something like that. If you just want to have a bunch of things, vector is almost always the right choice. So, it's C++'s version of a dynamic array. So literally every programming language that you're going to use is going to have something like this. All except C, which for some reason doesn't have this in the standard library, isn't built into the language. You have to write this yourself in C. But every other language either has something like this built into the language, or it has it, like C++, readily available in the library. And the fact that it's an array means that its variables are laid out sequentially in memory. So again, if I had my whiteboard, I'd draw you a nice diagram of how these things are just laid out. If you have a vector of ints, then they're literally laid out in memory, int. Right? Sequentially laid out in memory, as opposed to, for those of you who know about these things, as opposed to a linked list, where you have one element here, which has a pointer to the next element, which might be over here, which has a pointer to the next element, which might be over here. Linked lists have their place, but they're generally slower, for most things, slower than vectors, slower than
CPU caches are important.
arrays. Yes.
So like you have like a list of 1, 2, 3, like a collection of 1, 2, 3 numbers 1, 2, 3. Yeah. The first one is then, let's say, a memory address 1. And it's sequentially in memory, or sequentially like 1, 2. So like, let's say the address is just 1. I'm just making this up. Yeah. And 1 is linked to 1, and then 2 is linked to 2.
Are we talking about linked lists, or are we talking about
this list?
Value isn't linked to the address. The address is wherever you can find free memory. What you store in the address, so the number 2, has nothing to do with the actual address it's stored at.
It's not so. It's not like sequentially placed in memory. Like each container or the whole container is placed in one place.
In a vector, each number is stored sequentially. What those numbers are is whatever you want them to be. So you can have a vector of int, and the first element is 1, the next element's 100, the next element's
So-
5,400.
So let's say that the first element in your vector is given. It happens to live at memory address 20, right? So if you were to get a pointer to that first element and print that pointer out, it would tell you that this is address 20. What it guarantees is that the next element,
21.
well,
It's not.
however many bytes, there are 4 bytes in an int, so it would be 24. Right? But yes, it's guaranteed that it's laid out directly after it. So yes, as I was saying, vector is like a handle that manages a dynamic allocation for you. So effectively the number of elements you can store, at least on a 64-bit system, is limited just by the amount of RAM. You can have billions of things in a vector if you really want to. So the fact that the things are laid out sequentially, that it's a dynamic array, it means it's really fast. But fast random access means that if I want to access the 10 millionth element of a 20 million size vector, I can do that in constant time. I can do it really fast. I can iterate through things really fast. I can add new elements to the back of the vector very fast. And on top of all of this, it provides good locality of reference, which means that on modern CPUs, it makes really efficient use of the CPU cache. So if you don't understand what all those words mean, don't worry. It means vectors really fast, right? That's what it boils down to. This is why vector is the container you almost always want to use.
Constant pending.
Yeah, constant time at the back.
To reallocate.
Amortize constant time.
Oh, there you go. So the idea is if you fill a vector of stuff, once it runs out of space, you reallocate.
Oh, do we get to that?
Sorry.
But let's talk about constructing a vector first of all. In fact, before we even get to that, let's talk about how we get access to vector. So again, we have this horrible include system, including headers. The standard vector is contained in a header called vector. So we hash include vector in angle brackets. Just like if you remember the examples, we could hash include string to get access to the standard library string type. So we need to put this at the top of our source file before we start using vector. So this is really standard C++. And to actually create a vector, we need to tell the compiler what kind of elements we want it to contain. So we do that by writing standard vector and then putting the type that we want in angle brackets. So here we've done standard vector, angle brackets, int, vec. So vec is a vector of ints. Does that make sense? So we can have a vector of strings.
If you want to put different type inside, so we just
So you could-
update.
What do you mean by different types?
So you could have a standard vector of float or a standard vector of
Int and
Yeah.
float.
Sorry?
One
Int
and two.
float.
A single instance can only hold one. So this will only hold int. You can't make it hold something else as well. You can make a new vector of float, and that one can hold floats.
Yeah.
Now, if you wanted to get complex, you could use polymorphism because you have a base class, and then you have implementation.
A
So
vector can only hold.
hold different kind of type.
No, a vector can only hold one. A particular vector can only hold one kind of value.
Okay.
In C++ 17, you could have a vector of stood variant of possible types. Stood variant would give you that functionality. You could have a vector.
Oh,
of
you could
those.
have a vector.
It's like layering different features.
You can have a vector of any, or yeah.
Yes.
Can you define auto in the vector? Like auto when you want.
Oh, you mean the template?
No, you actually can't. Which is strange. You'd think they would be able to, but no, you're not allowed to. In C++ 17, they do. There's this feature called compile. What's it called? Constructor template argument
Deduction.
Anyway, it lets you omit this bit and deduce it from the initializer. So it's like as if you put auto there. But again, that's a 17 feature. We're not doing that quite yet. So that's why I've said.
And it wouldn't work there because there is no constructor.
Yeah.
You get type to figure out.
Because I was bad and I didn't initialize my variable. Not that it matters
I'll
with
ask
that.
you about that.
Yes.
Is that a common way to initialize a vector if you don't know what you're going to put in it yet? Or do you need to initialize it with something newly? And if so, how?
So, having just lectured you heavily on always initializing your variables, I really should have put an empty pair of curly braces there.
Well, it's static
However,
lifetime variables are initialized.
well, let's pretend this is inside.
It's not about lifetime.
Let's pretend this is inside a
This
function.
has a default constructor and it will use the default constructor. For trivial types like int, they don't have constructors, but for this, it has an actual default constructor. Which is their
In this particular case, it's all right because I know that int has it.
If you know the size, if you know your size of your vector, is it worth giving it a size when you initially define it?
Yes, we'll come to that in a couple of minutes, in fact. But just to go into a bit more detail, so this is a standard vector is what's called a class template. So if you've heard about C++, templates are scary and really powerful. But in this case, just using them is relatively easy. So again, if you've done any Java or C# or whatever, this looks quite a lot like using generics. And it works quite a lot like using generics. But there's one key difference, is that this thing, the element type, the value type, is part of the vector type. So this is different from if you've used generics in Java. So standard vector int and standard vector float are different types.
Question from the internet. How can vector be sequential if they are dynamically allocated?
Because it allocates a really big chunk of memory, and when you fill that up, it creates an even bigger chunk of memory, copies all the stuff from the first allocation, destroys the first allocation, and then, which again is something I would have drawn on the board if I hadn't.
Try to move it. Try it this way.
Yeah, it moves it.
Yeah. For trivial types, that's meaningless.
So this is where I was talking about the difference between using curly braces and using round brackets to initialize things. Really, vector's the only type where you have to worry about, well, one of the few types where you have to worry about that. If you use curly braces, this is what's called Lisp Initialization. So I'm saying I want to initialize vec1 and I want to give it the initial elements 1, 2, and 3. So vec1 is a vector of integers and we're initializing it with 1, 2, and 3. That make sense? Yeah. List initialization. Or in this case, I've got a vector of strings and I'm initializing it with hello and world.
You need to include strings.
I would need at the top include vector and include string, yeah.
So you don't need to mention that how many elements can be inside the vector?
When you use this, no. It looks at your initializer list and it works it out. It says, okay, this thing is called an initializer list. So it would look and it would say, okay, I've got 3 things, so I know. Yeah. And here we go, okay, I've got 2 things that I need to initialize, and it would construct the vector of the right size.
What if you accidentally put an equal sign there?
An equal sign in there, that would actually be fine. That would work. Yeah. Yeah.
So is it just along my comment? I don't know if it's useful. I just want to know, is it a C++ feature to allow these different expressions, or is it?
I don't know if feature is the right word because feature would imply it being positive. I think this is. I think this is actually just having more than one way to do the same thing means that there's more possibility for bugs. I think often. But yes, the fact that you can put an equal sign in there is sort of for backwards compatibility with C, which is because it's how you have to initialize aggregates in C. And this syntax is supposed to make vector appear a bit like it's a C aggregate, or by which I mean like a raw array in C.
Basically, we add an equal sign. any of those answers?
No, because you can't use the equal sign with round brackets. You can't do equals round brackets. Or you can if it means something that doesn't mean what you think it means.
Due to magic in the standard, when you use equals, it invokes operator equals, which is defined inside std vector, which takes a std initializer list, which is then able to handle that curly brace thing. It's all horrible, horrible magic that is very nasty to sort of grasp until you're further along with C++.
So this is one way of doing it. We can give it some initial elements. But another way of initializing it is to have, this is what you were asking, an initial count of elements. And if we want to, a default value as well. So, give an example of that. This is a standard vector of int, and now we've used round brackets. Not these curlies, round ones. And so this is a vector containing 10 million zeros. So had we put curly brackets here, what would happen? One item whose value is 10 million. But we've used round brackets, so we're calling the constructor that says, can I have 10 million copies? So it would be bad if we wanted to have one element that had the value 10 million, and instead we've gone and allocated a 40 megabyte array.
Probably worth mentioning as well that the single quotes are also a C++ 11 feature that said you can use this as a decimal separator.
Oh yeah. I mean, this is
just readability.
This is just to make it more readable.
Sorry, these 10 million zeros, where are the zeros coming from? Like if you was doing 3, for example, what 3 means? 3 zeros? Yeah?
So the default value is optional. So if we want to show with a default value, and we can say this time we've got a vector of strings, and we say we want 10 of them with the default value hello. And now vec2 contains 10 copies of hello.
Is there a good practice? Is it like when you initialize, is it better to just give it like the 7 and a half 5 elements, or to just give it the actual elements? Or does it not matter?
It depends.
Yeah, if you know the initial elements, if you know that your vector should have 1, 2, 3 to begin with, then just put that. You obviously don't want to use this syntax to write out 10 million zeros, right, in curly braces. That would take quite a while in your source code. So this is the better way to do it in that case.
There's an important distinction, but I'm going to let you get into reserve before I mention.
How can call the element of the vector inside the vector if I want the first element?
If you want to access the first element of the vector, I'll talk about that in next slide or the one after that.
So I'll have to use
No worries.
So basically, bracket is used when you are sure that all the elements are the same, and you know the number of the elements.
So almost the other way around. So with vector, the curly braces are used to give it initial elements, to give it a list of initial elements, and the round brackets are used to call what are called other constructors, other functions that make a vector. So these are 2 examples, but there are actually quite a few other constructors that if you look at the reference documentation, I haven't gone into them because they're not used as often, but there are a few other different constructors that you can use.
It's still possible to call them by the curly braces, but it becomes a foot gun because you can think you're initializing.
No, I don't think it is.
Do you think it's possible at all?
No, not when you've got a standard initializer, this constructor, this...
Can you override it?
Yeah, everything's set. Copy construction, default construction.
Does C++ have an equivalent to Lisp comprehension or vector comprehension, I guess it would be called? So you can generate, using that method with the parentheses, you can generate a defined list of any single value, but can you generate a defined list of values that you can compute given a function?
There is not
Or
Not built into the language, no. There is a function called standard generate. It's put in the standard library, and you can give it a vector, and you can give it a function of a lambda function that, as you run that, it will fill the vector with whatever. So, vector is a dynamic array. That means we can change its size. Means, in particular, we can add things to it. And to do that, we call the pushback member function. So, most languages this would be called something like append, but C++ we have to be different. So it's pushback. Push a new value to the back of our vector. What? Member functions, we haven't talked about them. They're often what are called methods in other languages. Well, I'll also use the term methods, but properly, strictly speaking, proper term in C++ is member functions.
Pushback is putting the element at the end.
Yes.
So it's like add.
Yes, add or append. Yeah, stick it on the end of the list.
Append going in the front. No?
There is no push front, so the equivalent would be push front, right? To put something on the front of the vector. There isn't a push front function for vector.
It's definitely go in front.
You can do it. You have to use another function called insert, and it's a bit more ugly to do it. And the reason this is a deliberate choice. They wanted it to be ugly because adding things to the end of a vector is very fast. Adding things to the beginning, if you imagine you've got things laid out linearly in memory, you want to insert something there, it means you have to take all these things and shift them all down one space in order to create a new space at the top. So that's really slow compared to just sticking something on the bottom. Right, so for that reason, yes, they let you do it, but they make it hard to do, so you don't do it by accident. Right, so that's why there's no push front.
Basically, just use the vector in reverse order. So just think about how you're using it, right? You don't need to make the container do things in reverse order. Your logic can do things in reverse order. So that the item at the front, you consider to be the last, and the item at the back, you consider to be the first. So just think about it differently. You can organise your code so that you achieve the same goal with memory efficiency.
Like a stack.
Somewhat like a stack, yeah.
So there's a pushback, there's also a pop back. Pop things off a stack. Well, yeah, exactly.
It is a stack, isn't it? It's not like it is a stack, right? Because you're pushing it to the end and you pop. First in, last in, something like people, first, last in.
Yeah, essentially last in.
Yeah. So we use pushback to put things on the end, pop back to remove the last element. I'll give you an example of that. Here we've declared a vector of int. It's got 3 things in it. 1, 2, and 3. We call vec.pushback. So this is a member function, a method. We call it with this dot syntax. Pushback 99. And now vec contains 1, 2, 3, and 99. Yeah, and then if we call pop back, we remove the last element, we remove the 99 we've just put in, so it's now just 1, 2, 3 again. That make sense? It's all pretty straightforward.
Is it better to use a C-style array if you're in a situation where you want to arbitrarily put things in indices?
No.
No. Okay. So would you need them? How would you do that?
Wait, just one moment. Oh, everything's gone really tiny on this slide. Sorry, can you read that at the back? No.
We can ask a vector for its size.
Hang on. I'm gonna split this onto a second slide because everything's
Number of elements.
Everything's gone really tiny.
Size, square brackets.
I'll be with you in one moment.
Can we call index in the vector and add something inside one index, or you need to
Do you mean like insert an element in the middle or something?
Yes.
Yeah, absolutely. So are you going to cover iterators on this bit?
No.
No. So there's a feature, there's something called iterators. So an iterator is something you can add to and subtract from, and it sort of iterates through the elements, right? And then there's an in place or push member function on vector where you give it an iterator, so the iterator points to a position, you give it what you want to stick in, and then it will, obviously behind the scenes, that could obviously possibly be expensive, but it can then allow you to do it.
So, like I was saying about inserting something at the top, if you want to insert something in the middle, it's the same thing. If you insert something in the middle, everything below that has to shift down one space.
Yeah, sure.
Yeah. So again, if you've got 100 million things that you have to shift all of those down one space, that can be quite a costly, quite a time-consuming thing to do. So in general, you want to avoid inserting into the middle of a vector, a large vector.
But sometimes you need to sort, for example, and do you have sorting vector?
Yeah. But if you're sorting, you don't insert anything into the middle, you're just swapping elements around. So that's it's a bit quicker. But let's talk about size. You can read this now, right? Yeah. We can ask it. We can ask a vector of size. A vector knows its own size. That's one of the things that makes it better than a C array. And we can just say vec.size. And here, you remember the assert function from a few weeks ago. Assert basically crashes your program if that condition's false. So we assert vec.size equals 3.
Is it a separate, is the size of an actual separate property of the class vector, if that is the right terminology, or does it, when you call size, it computes its size?
Technically, all the standard says it does it in constant time, right? And really, it doesn't matter whether it stores that as just the size as a member variable, or it can do it by subtracting the start pointer from the end pointer. It really doesn't matter because it's going to be in a single step anyway. So we have a size, but we also have a capacity. So the way vector works is it normally allocates more memory than you actually need. Right? So as you add a new element, let's say we've got this is what I really want. Right? You've got 3 elements in your vector. You try to add something new to the end. It's going, okay, I've got no memory left. So it goes to the operating system. It says, please can I have more memory? But it doesn't just ask for enough space for one new element. Because otherwise, every time it did that, every time you added something, it would have to go back to the operating system and say, can I have space for one new element? Can I have space for one new element? And it'd be really, really slow. So what it does is it asks for space for loads of new elements. In fact, usually double the number that are currently there. So if you've already got 3, you add something new, it'll say, okay, I need more space. Can I have enough space for 6 elements? Right? And then when you fill those up, it'll ask for 12, it'll ask for 24, etc.
Will it ask for the previous size or the size plus 1?
No, it'll generally ask for double the previous size.
Okay, so if it's 3, it will ask for 6, not 4, then 8.
Or 4 and 8. Right, so if you've already got, so if you initialize, here we've initialized it with 3 elements, that's why I use that.
Yeah, so now will it ask for another 3, not another 4?
Well, it's generally it will double the existing capacity.
Okay.
This is an implementation detail.
Yeah.
So
it's not guaranteed. In fact, one standard library does it at a factor of 1.5 rather than double for sort of weird reasons. But this over allocation, allocating more memory than you actually need right now, is one of the features that means that adding things to the end can be in called amortized constant time. Makes it really fast. Because only rarely, and increasingly rarely, do we have to go back to the operating system to ask for more memory, which is a slow process. So we've got now 2 properties of the vector, or 3. If you include the elements, we've got the size, we've also got the capacity. The capacity is how much spare space do I have, or in fact, how much space do I have altogether. So the spare space is the capacity minus the size. This, how many more things can I add before we have to reallocate? And, oh, I didn't, this was my new slide, I didn't make it appear a bit at a time. But we can ask the vector for its capacity using the .capacity member function. So if you try this, if you say vector int is an empty vector, and then we add 1, we add 2, we add 3, what you'll probably find is that its capacity is 4 at this point. Because it's overcommitted. Allocating more, because it's thinking, okay, you're adding things, I'll give you enough space for that. And then if you add in a couple more things, its capacity might jump to 8.
That seems like the implementation detail system, right?
It absolutely is. And those numbers that I quoted, that's typical, but it's not guaranteed.
So from the application point of view,
Why would you bother
to know?
Why would you bother to know? Because sometimes you need to reclaim that extra memory back, right? Because if you've got 21 million things in a vector, right? But it's gone and allocated enough for 40 million. That's quite a lot of wasted memory, right? If you know you're never going to add any more to it, so you can reclaim that memory using this member function called shrink to fit. And that will set the capacity equal to the current size.
Sorry, why the capacity is 4? Because you have 3 elements, so the capacity should be double, like 6. No?
So let's imagine what we're doing here. We've got an empty vector, and then we add 1 element.
The capacity is 2.
So, well, could be, yeah, okay, so capacity is 2. And then we add a second element, so we filled up the vector, that's fine. Now we're adding a third element. So it doubles its existing capacity. Its existing capacity was 2. It doubles that, so its new capacity is 4.
Oh, okay. So the capacity might be full.
Might be full, yeah.
Oh.
In which case it'll reallocate if we add 1 more element. We can use this if we know in advance how many elements we're going to add to the vector. If we know we're going to add 10 million things to it, we can call this reserve function to say, okay, please can you set your capacity to 10 million? And that can save you doing lots of reallocations along the way. It's something that should be used sparingly. It's one of these things that is there kind of for optimization purposes. Generally, you don't have to worry about it, but we'll do. I can bring it to your attention.
Right, if you know exactly how much you need, I kind of recommend it. I mean, if it's a trivial amount of stuff, then fine, don't bother. But if it's only getting fairly large, do reserve.
How do you know?
Well,
depends on your use case.
The drawback to reserve is you can get into n-squared allocation problems with it.
If I reserve, it's 1 allocation. If I rely on the standard library to figure things out for me, it's probably going to be at least more than 1, right? Another thing to note with reserve actually is that it won't ever shrink it. If you give it a number that's smaller than what you currently have, nothing happens. It will only ever make it bigger. Only shrink to fit will actually make it give the memory back.
How do you actually reserve it? Do you reserve it in bytes? Or
So let's say up here,
number of elements.
Yeah, up
so
here,
elements.
up here. Just imagine in there, in between this one and the first pushback, we say, okay, well we know we're going to add 3 elements, so we'll call vec.reserve brackets 3.
Okay.
And that sets its capacity to 3, reserves enough space for 3 elements, and then we pop the 3 elements in there, and now vec.capacity will be 3.
Once you reserve, you can still add them?
Yes. Yeah.
Can you deallocate this reserve 0 to release memory?
No, but there is a function, there's a function called clear, which deletes all the elements, but I believe leaves the capacity unchanged. So, as Ollie just said, shrink to fit is the only thing that will ever reduce the capacity of the vector. So, there's .clear, which clears the vector, deletes all the elements.
So I saw something called erase.
That removes a range or a single element.
So erase, you can say remove the element at position 27. Or remove all the elements between position 27 and between position 41. Or you could erase the whole thing.
Erase vector
Yeah. You can erase all the elements, but it doesn't affect the capacity. So erasing all the elements is the same as calling .clear. It deletes all the things, but it leaves the capacity unchanged. So then you would have to call shrink to fit to reclaim that unused capacity.
Obviously, using arrays with .begin and .end is pointless because you can just all clear and it's less code and it's more obvious what you're doing.
So we tried that when we came to when you do the size of after arrays.
Size is different from capacity.
No, sorry, size.
Yeah,
that would be zero.
It crashed because the array wasn't there, the vector wasn't there.
Then if you crashed it, you did something undefined. You must have introduced a bug.
If you use clear, then it worked.
Then you did something. Then whatever you passed to arrays must have been incorrect, and you
I have to check.
Okay.
Because it should.
Okay, that's fair. Yeah, I mean that's at my memory. So.
Were you going to say something? No. Where am I? So let's talk about element access, which people have been itching to.
Sorry, the size of.
Size of. Size of is a completely different thing. Size of is something that's built into the language that tells you how many bytes of stack space does this occupy.
Okay.
It's a very low-level function that you don't really have to use too often in C++.
Is size of actually giving you the data type and saying how many bytes you have?
Yeah. So what I was talking about standard vector being a handle to some dynamically allocated array. If you say size of vector, it will probably tell you it's 3 or 4 pointers in size.
Yeah, that was where I
That's
was
the
confused.
yeah.
Because every single vector here gave a size
Gave us
of
the same
24.
answer. Yeah.
Yes, exactly.
Yeah, because the stack capacity, the size of the handle is fixed, and that's what size of tells you. It tells you that the number of bytes that it holds. Yes. Correct. Yes.
It tells you the amount of space that the vector occupies in order to do what it needs to do. It doesn't tell you anything. You pretty much never should be doing size of one vector ever, unless you're like doing some manual memory management lunacy. No, just no.
Size of is more for size of int, size of
Yeah.
byte, size of boolean.
So size of will tell you that an int occupies 4 bytes of memory. Why is that useful? Well, it's useful if you're doing like really low-level C routines where you need to copy raw bytes around. For the kind of C++ we prefer doing, where we're doing nice high-level work and using these nice abstractions like standard vector, we won't touch size of.
So size of an object doesn't give you anything useful.
Well, it tells you how many bytes of stack space.
If I wanted to manually allocate space for a vector, then I would use size of vector and then call malloc, but we're not doing C, so don't.
No. That's only using that OpenGL.
Element access. You have to. Oh no, we're nearly there. We're almost there. It's linear array in memory. Things are stored in the order they're added. So it's not like a set where things things are stored in a sorted order. It's a list. Things are put in the order that you add them. And this means that every element has an index counted from 0. So the first element has index 0, the next one is index 1, 2, 3, 4, all the way up to however many you've got. So we can access that element by writing the name of the vector, square brackets, and then the index. So to get the first element, we write vec, square brackets for the 0 in the middle. So here we've got the vectors 5, 4, 3, 2, 1, just to do something a bit different. And now we're asserting that the 0th element is equal to 5. And that the element with index 4 is equal to 1. So this is 0, 1, 2, 3, 4. when you're doing this, you will get it wrong. Just till you get, if you're used to counting from 1, this is going to seem really strange. Counting from 0, you will make mistakes with it. It's something that you have to live with, and even experts have what's called off by 1 errors. This counting from 0 is a bit strange, but you can have a range for loop, yeah. Wouldn't that be better than, well, if you're doing something for every element of the vector, of course. If you just need to access a specific element, then this is how you access. And the nice thing about this square brackets operator is that it returns you a reference to that element. Not a copy, a reference. And that means we can assign to it. So we've got, again, a vector containing 5, 4, 3, 2, 1, and now we're setting the element of index 2 equal to the value 42. So it's 0, 1, 2, so we're changing this 3 here into 42. So now the vector contains 5, 4, 42, 2, 1. Yeah. Sorry.
Just if you assign like 42, comma, 100, comma, 100.
Yeah, semicolon.
Yeah, semicolon. Is it going to interpret it as 3 elements, or is it going to?
Comma. No, that would be a comma or break.
So what it's going to do in that case, believe it or not, that will compile, which is stupid, but it will compile. And what it will do is it will actually assign the last of those 3 things. It will assign the value 100. Yeah. There is a way to add multiple things to a vector at once, but it doesn't use the square brackets.
Because earlier you showed that C++ allows you to use the comma as a
But that was a single quote. That was a single quote.
Oh yes, sorry.
10 million.
In the 10 million example, that was an apostrophe, a single quote, and that was just used to separate out digits to make it more readable. So that wasn't using a comma at all. That wasn't comma.
Yeah. And if you remove them, the code would be exactly the same. It's just for human readability.
Oh, how much more have I got? Am I going to finish on time? Oh, one more slide. That would be all right. Oh, again, it's gone quite mini, but it's gone really mini. But this is just what we were saying. You can use things in a range for loop. Let me just sort this out.
Can you assign to an index that hasn't been assigned to yet? Like
outside of bounds?
Yeah.
No, that's undefined behavior.
So you'd have to push back to get.
Yeah.
Correct.
Yeah, so where am I? This syntax is the index, the acceptable indexes are between 0, you can use 0, and 1 minus the size.
Which is the last
thing
you push back.
Yeah, exactly.
Unless it's empty and then 0 is not acceptable.
Oh, well, yes. So, oh, sorry.
I was saying that it seems the resize allow you to
Dot resize.
vector dot resize function allow you to actually.
Yeah. So resize fills in the extra with the default value for whatever the value type is.
So you can kind of dynamically size the.
It will kill existing elements from the end backwards, but it'll also add new elements, default initialized. You can make it bigger or smaller, as you wish.
Right, so this is what we're talking about, range for loops. We actually gave this example few weeks ago when we were talking about range for loops, but we go through it again. Vector is the archetype of container really for this for ranges. So here we've got a vector of 1, 2, 3. Now we're doing 4 auto I. So for each I, which we've used the deduce type, colon vec. So for each I in our vector, I'm going to print I and then put a space after it. So as you might expect, this prints out 1, 2, 3. So this, you could write this as an old-fashioned for loop with the 3 elements, and then use the square brackets inside it to generate exactly the same thing. But this is just a nicer bit of syntactic sugar. Makes things nicer.
You know, speed. Why you use auto?
Good question. Because I wanted to. This is going to go to it. I wanted to just show you that this is actually a slightly bad pattern to use. Oh, no, I'm too far. If this had a really long type name, then auto just makes it easier to write. But the problem here is that auto is never a reference, which means that as we go through the container, we're copying each element into our loop variable. Now for an int, that's not a problem. An int is fine. But if it was a string, if it was another vector, because a vector can contain another vector, two-dimensional things, that copy would be expensive. It would be something that we don't want to do. And in fact, you can have a vector of types that can't be copied. Yeah, in C++, we haven't talked about them yet, but there are types which can't be copied. And in that case, this wouldn't compile at all. So that's why I used auto in this case. So it's almost always better to use auto ref when we want to change the elements, and const auto ref when we don't. So now I've written this little function called fill vector. So this takes a vector of ints by reference, right? Returns nothing. Its argument's parameter type is a vector of int reference called vec. So I'm creating a local variable called value. And now in our for loop, we've got auto reference I in our vector. So for each element I in our vector, we're going to assign I whatever this is and then bump the value of this. So if we give it a vector of 1,000 things, this is going to replace all those things with 0, 1, 2, 3, 4, 5, 6, all the way up to 1,000. And again, you can imagine writing this for loop with, int I equals 0, I less than vec.size, blah, blah, blah. You could imagine doing it that way instead. I think the for loop makes it a bit easier. But this thing, if you're going to modify the elements, use auto ref. If you're not going to modify the elements, use const auto ref. There are, Ollie's itching to say, I'm sure, there are a very few number of situations where auto ref doesn't work, but 99% of the time it's the right thing to do. Yeah. 99% of the time it's the right thing to do.
You just do auto around there.
Really, can of worms were open? No. Right, there was supposed to be an exercise now. We have obviously run out of time, but timed it just perfectly because it's 10 seconds to 9 o'clock. So we might do the exercise next time. Otherwise, I will put the slides on. Yes, they're homework if you are quite interested in doing these things. Chapter 18 has one of these drills that I quite like because it takes you through doing things step by step. So there's one at the end of chapter 18 in the textbook. You can do that if you like. Oh, sorry.
What was the textbook again?
Oh, yes. It's called Programming Principles and Practice Using C++.
Bird book.
In vector
Yes, yes, you can. But it actually has something a bit better, which are called iterators, which work a bit like pointers to elements, but are sort of more powerful in some ways.
It's somewhat awkward when you first discover them.
Yeah.
You didn't use the auto.
Sorry?
You didn't use auto. Would that still be a copy or would that be
Int and.
If it said int, it would be a copy. If it said int ref, it would be a reference.
But you were saying that if you just use the bracket, it's always automatically brackets, right?
If I just use the brackets.
The brackets operator.
You mean the square brackets access?
Yeah.
Yeah.
So, and you said the foreign group that is actually syntactic, syntactic sugar.
Okay.
So they should be the same exactly. Why is one using reference, one using
No worries. Okay, so if we do, this is our handwritten whiteboard, so
yes, I'll probably over when I'm
I'll give it back to people next week. The thing is, like, they don't let you export it, so what I can do is I can video through a screenshot everything.
okay, so we have this nice range for loop here, for int I colon there.
Yeah.
Now this gets translated into something that looks a bit like.
Just waiting.
Just right now. For
Now you have laptops.
this is not 100% correct. So what it does is it basically translates this into a form. Now it doesn't, just to stress, this is a schematic, which is not exactly what it does, because it doesn't use indices, it uses iterators. So you can imagine what it's doing is it will create, every time you go through the loop, it will create this thing inside. It will use exactly what you put here. And it will assign it the element of position k. Right, so I've used k as my loop index here.
But if you don't mention what is the size of vectors, how do you know what is the size minus 1? Because your regular, when you identify a vector, you don't mention the size.
When you
When you create a vector, you don't mention the size of the vector.
Zero.
When you just write
zero. The vector always knows its own size.
if I just use vector of int b.
How do you know the size?
Oh, because the vector stores it as part of the vector, part of its data. It's one of the properties of the vector. It always knows its own size. So you can ask. You can
Okay,
say,
everybody.
size.
Whoever wants to join us, we're going to pub. So you're very welcome.
Just run it for one of you. We'll treat so you can't stagger or anything. Right. Oh, wait.